I'm searching for supersymmetry in the 3 lepton channel at the HL-LHC. Boone, UBC.
Hi, so I'm Kyle, and he just told me the topic of my presentation. So I was working with a group here at UBC led by Dr. Colin Gay, and I was over at CERN for part of the summer working there on this project. So the title is a bit intimidating, so I'm going to break that down for you. So we're going to start by talking about the physics. So the standard model of physics and supersymmetry. What the process I'm looking for is called direct gauge genome production, specifically. Then the experiment itself. So it's the Atlas detector, and I'm looking at this at the LHC and at a proposed upgrade to the LHC called the HL-LHC. I'm going to talk about the background processes we have to deal with, which are WZ boson production and TT bar production. And a big problem in particle physics is separating a signal from background. To do this, we use machine learning and boosted decision trees. And when you combine all of this together, we end up with results, which are the sensitivity of the Atlas detector to this model at the LHC and at the HL-LHC. So, the standard model of particle physics. I'm sure most of you have heard of this before, and if you haven't, I'll just give you a brief introduction. So, the standard model of particle physics explains electromagnetic weak and strong interactions. It predicts a bunch of particles, which you can see up here. So there's the quarks up in the top left, the leptons here, and a bunch of force carriers. And there's also the Higgs boson, which I haven't shown here. And up to now, all of these have been observed one by one over the years, and up to what we think is the Higgs boson, which was found earlier this summer. But the standard model itself, it works great, but it has some serious problems. So the first is there's dark matter. We know nowadays that the normal matter that we see is only 4% or something of all the matter in the universe. And dark matter isn't explained at all by this theory. There's also something called the hierarchy problem, which is the fact that the Higgs boson, if you look at all of the particles in the standard model, slight corrections to any of them can make the Higgs boson mass jump by something like 10 to the 30 GeV, when it's only 100 is what we see right now. So this is bad. And supersymmetry is a way that has been proposed which can fix all these problems. So supersymmetry predicts that for each particle that we see in the standard model, there's a supersymmetric pair particle. So if you look at this model right here, what this means is for all of our quarks here, we have what are called sporks. For all of our leptons, we have leptons. For all of our gauge bosons, we have gaugeinos. And they get all sorts of silly names, like the top quark gets its pair, which is called a stop quark, or things like that. And physicists are very good at naming things. They have a lot of fun with that. So if we want to look for this model here, supersymmetry, there's all of these particles that we can find. And, well, really, we just need to find one to find evidence for something. That would be a good start. So when they turned on the LHC, what they were looking for was these guys up here, the quarks. All of them except the stop, actually. And they thought they'd find them right away. But when they turned it on, nothing. And the limits that they have on these are masses of something like over a TeV are the limits right now, which is really high. And that's not very good for supersymmetric models in some ways. But because there's so many different particles, we need some which are light in order to fix the hierarchy problem that I talked about before. So right now, people are looking a lot at the leptons, seeing if we can find them, if they're low masses. And a lot of work, too, is going into over here, looking at the gaugeinos, these guys, and seeing if we can find them. So my project was to look for something called direct gaugeinos production. So if you look at all these here, there's a lot of particles, and it gets even more fun because in quantum mechanics, they can mix together to form these eigenstates for a mass, which are not these particles you see here. So the photino and the Higgsino is what they're called. They can combine to form these new particles. So what we assume is that we have 4 neutral particles and 4 charged particles, 2 of each sign, that we might be able to find. So what I'm looking for is a process where we have these all of these particles here are really, really heavy, and these are two neutral particles called neutralinos, or light, along with one of the charged one, called the charge E. So, in this case, we end up with models like this. So here is a Feynman diagram. I'm not sure how many of you are familiar with those, but what happens is you've got time here going from left to right, okay? So here we've got our two protons coming in, because at the particle accelerator we collide protons together. They form a W boson, which then decays into the chargino 1, that charged supersymmetric particle that I talked to you about, and the neutralino 2, which is the second lightest of these neutral supersymmetric particles. And these decay with these interactions here. You don't really need to worry about it too much. And what we see, so on the right side is what you're actually going to see in your detector. All of these interactions happen very quickly. There's no way to really observe them or anything. But you'll see these particles in the end. So the E's that you see there are electrons, or muons, it doesn't really matter. And so there's 3 of them in the final state. And you also get two of these neutral supersymmetric particles and a neutrino. So the neutral particles don't interact, or these neutral particles don't interact with our detector at all. So all you're going to see is 3 electrons after you collide these 2 protons, and a bunch of missing energy, because you can do your you know that there was no momentum in the plane perpendicular to your collision. So if you add up the momentum of all of the particles that you see, and it doesn't add up to 0, then there must be something missing that you didn't see. And in fact, these supersymmetric particles are stable. I won't go into the details of why that's the case, but they're our dark matter candidate, and they could potentially be, well, yeah, if they're produced, they'll end up firing out from the detector and just going forever, not interacting with anything. So, how exactly do we look for this model? Well, we've got this big particle accelerator in Switzerland called the LHC, which I'm sure many of you have heard about. So the LHC is the world's largest particle accelerator right now. And the Atlas detector is a general purpose physics detector which can look for pretty much anything that the LHC produces. So the HL-LHC is a proposed upgrade to the LHC. So in case, like I showed you about in that model, there's a lot of particles that we can find, but if nothing, well, upgrading the LHC lets us put higher limits on these models and detect more of what would be done. So the LHC is predicted, or is going to collect about 300 inverse vectorbarns of data. That's just a way of measuring data. And this proposed upgrade would get up to 3,000. So I was investigating the sensitivity of the LHC and of this upgraded version of the LHC to the model that I was talking about before. So, if we're searching for the signal, what do we have to worry about? Well, the standard model itself has lots of processes which can produce the same signal that we see, of 3 leptons in the final state. So if you look here, this is a process called WZ production. And cross-section up there really just means how many of these we produce. You multiply cross-section by the luminosity to get the number of times you expect to see this. So this happens about 5 to 500 times as much as our signal. And if you look at this, we get 3 electrons and a neutrino, which is kind of exactly what we saw before. So it's a bit tricky to separate this from our signal. But if you look, there's only the neutrino here, whereas in the other one we had those neutralinos. So there's a lot more neutral particles that we don't see in the signal that we're trying to look for. So if we look at the amount of missing energy in the transverse plane, when you add up your momenta and see that it doesn't add up, then the signal will have a lot higher of that value than this model, or than this process will. You also have something called TT bar production. So it's producing a top port and an anti-top port. And this happens a lot at the LHC. If you look at the number there, it's 1,000 picobars, which is like 100 to, I don't know, 10,000 times what our signal is, so it happens a lot. But in our supersymmetric signal, we had a Z boson, which was decaying to electrons. And if you cut for that mass, you can just completely annihilate the signal, which is good. However, when you actually start making the plots, so I was telling you that we can use this missing energy, right? If you look here, well, the signal is all these points here. That's a few different signal points. And that black is our background. And, you know, when I look at that, I don't see much way to pull my signal out of there very easily. So what we have to do is go into machine learning techniques. So what these do is you tell your computer to essentially, you train it on Monte Carlo data and use this to optimize a way of selecting your signal out from your background, using all of the variables that you know, like this missing energy, and there's like a dozen other ones that I ended up using in the end, to try to separate your signal from your background. So if you look here, this is kind of, I use a technique called boosted decision trees. So what you do is you make these trees like this, which will pick a variable, make a cut on it, and look if that cut helped improve your signal or your background. And you get these trees which end up essentially splitting your events into bins, which are either more background-like or more signal-like. And you make something like 1,000 of these trees and have your computer optimize it in order to separate the signal from the background. So in the end, this boosted decision tree outputs a score, which is will separate your signal from your background. So over here we have more signal line stuff, and over here we have more background line stuff. And the distribution for signal and background is shown there. And you make a cut over here somewhere, at which point you want to maximize something called the significance, which is your signal over square root of background. And that is what they talk about when you hear the 95% confidence level or 5 sigma that they mention in particle physics a lot. It's this significance or something similar to it. So when we do this, we end up with this beautiful plot here, which shows our discovery and exclusion reaches for this model. So at the LHC, it's these lines in blue here that we're going to have after a while. And at the HLOC, it's these red lines here. And these are the masses of our supersymmetric particles on the axes. So this result ended up getting published in a paper, promoting the HLOC because they're trying to get funding for it. And it's looking pretty good because this upgrade will have quite a significant increase on the discovery potential. So in conclusion, I investigated a supersymmetric model with low masses for some of the gauginos and high masses for all the other sparticles. We used a BDT to separate the signal from the background. And the HLOC will be able to exclude this model for masses of neutralino 1s up to about 400 or 500 GeV, discover it for masses up to about 300 GeV. And the results of this project are all public and can be found in this Atlas note here. Thank you.
Okay guys, now a couple quick questions.
So, what is your computing is left to decide the value of the cut in each of the parameters, right?
The decision tree takes in about 13 different parameters. So there's like the missing energy, the momentum of all of the electrons that I see, those 3 electrons or whatever. And it actually takes something like 12 variables and produces, it figures out how to cut on all of those variables.
Is it each variable individually? Or
No, so it cuts on all of the variables together.
Okay.
So it will find trends, such as if you have like high momentum in your first electron and low momentum in your second, then that's more signal-like than background-like. So it's a lot better than just doing a single cut where you're just looking at one electron and saying if this is high momentum. Yeah.
One more question, guys?
So you said that you need to sort of run some simulations to get your computer to look at what you're interested in. How long does it take to train the computer to make sure that you're looking at sort of what you want to rather than sort of all this other stuff?
So generating Monte Carlo samples takes a lot of effort. The LHC has something called the LHC computing grid, which is a 200,000 core cluster, which can just pump out samples like crazy, but it's a lot of computational work. The actual training, once you have all the samples set up, isn't that long. It takes like an hour or so. But yeah, generating those samples is